our colleague from Mexico, Professor Ramon Plaza, from the Institute of Applied Mathematics and Systems, IMAS, of the National Autonomous University of Mexico. So please, Ramon, thank you for accepting this invitation. Please go ahead.
Thank you very much. First of all, I would like to thank Professor Vladislav Kravchenko and Professor Alexey Karapetyants for the invitation to deliver a talk in this seminar. It is an honor to be here. I'm very happy to deliver this lecture. I'm going to talk about some instability results for kink and anti-kink profiles for the sine-Gordon equation posed on a Y-junction graph, and I hope that you find it interesting. This is joint work with Professor Jaime Angulo Pava from the University of Sao Paulo, and has been sponsored by agencies at UNAM and in Brazil as well. Well, let's first talk about the sine-Gordon equation and why is it important to pose this equation on a graph. What does it mean? So the sine-Gordon equation in one dimension in laboratory coordinates has this form. You all know this equation. This is a nonlinear wave equation. We're going to consider the sine-Gordon equation in one space dimension. And the name sine-Gordon equation started as a pun on the linear Klein-Gordon equation. The name remained, and now it's universally known as the sine-Gordon equation. As you know, this is an important equation in mathematical physics. It appears in many applications, in many situations. As far as I know, the first time that it was derived, it was in a book on differential geometry by Eisenhardt in 1909. In the study of surfaces with negative Gaussian curvature. But it appears in many other applications, especially in physics and also in biology. So it seems to be like a model, an approximating model that pops out in many applications. For example, in propagation of crystal dislocations, elementary particles, dynamics of fermions in the theorem model, in oscillations of a rigid pendulum, which is from elasticity theory, and in particular, in the propagation of a magnetic flux on a Josephson line, which is the application that we had primarily in mind in our study. So this is a model in superconductivity. Josephson won the Nobel Prize in physics in 1973 for his discovery of the Josephson effect. Suppose that you have the electric material that is in between two conductors. Then the phase difference of the wave functions of the electrons on one side or the other side of the dielectric satisfy the sine-Gordon equation. So in this picture, you have a two-dimensional Josephson junction, but you can also have that in one dimension. Actually, they are called Josephson junctions in 1D. Now, what is the motivation to pose a PDE on a graph? A metric graph is a shaped structure. It consists of edges, which are assigned a metric, a length in this case, which is one-dimensional, and they are joined via vertices. So these edges are connected at vertices according to certain boundary conditions, and these boundary conditions determine the dynamics on the network. Graphs are not manifolds, so actually the only coupling is given exclusively by the boundary conditions at the vertices, which is called the topology of the graph. This has been studied very thoroughly in the theory of quantum graphs, posed, for example, the Schrödinger operator on a graph bound by vertices, and even especially at the linear operators, no? But it has been also in recent years applied to nonlinear models. For example, in shallow water flow in a network, or nerve impulses in complex arrays of neurons. In our case, the sine-Gordon equation has been posed on a graph in order to design Josephson's junction networks. This is the work by Nakajima and collaborators in 76 and 78. So the sine-Gordon equation was first conceived on a Y-shaped graph by this Japanese group of researchers as a prototype for logic circuits. So they actually have some practical application. So you can pose the sine-Gordon equation on this graph, which has the shape of a Y, and then you can design a logic circuit. What is a Y-junction graph? So you have three long semi-infinite Josephson junctions coupled with one single common vertex. So this is also called in physics a tricrystal junction. I'm going to talk about Y-junction of the first type, which means we have one in common or parent edge, E1, from minus infinity to 0. This is a half ray. And it meets at one single vertex with other two children edges, AJ, which from 0 to plus infinity, J equals 2 or 3. This is a picture of this Y junction of type 1. As I mentioned, these are not manifolds. The only coupling is via the vertex. So you don't care about the angles here. You only need to pose the equation on this graph, on these two graphs, and then specify boundary conditions at the vertex. So let's talk about the sine-Gordon equation posed on a Y graph. So actually what you do is to pose the PDE, the sine-Gordon equation on each edge. For example, you will have a solution UJ, so a solution of this nonlinear wave equation on each edge EJ when J goes to 1, 2, or 3, okay? And the most important thing is to specify boundary conditions. So in our study, we consider boundary conditions either of delta type, which are specified here. As you can see, you have continuity of the phase. U1 and U2 and U3 are the same at the vertex, so the limits at the vertex are the same. And then you have these this condition for the derivatives. So minus C1 square U1 prime at the vertex plus the other two derivatives weighted by C square should be proportional to the value of U1. Here I have to say that the velocity on each edge is different. So we have a three velocity, C1, C2, and C3 on each edge. Excuse me. The other type of boundary conditions that we consider are called of delta prime type, which means that the fluxes are the same at the vertex. So C1 U1 prime is the same as C2 U2 prime, and is the same as C3 U3 prime at the vertex. And then you have like a Kirchhoff condition for the fluxes C1 U1 for the wave functions C1 U1 Cj Uj from 2 to 3 equals to some multiple of U1 prime. And here we have two parameters, lambda and z. Okay, so these are the two most general boundary conditions that you can consider, so that the operator is actually self-adjoint. Now, what do they mean? Lambda and z are given physical parameters. They actually measure the intensity of the interaction at the vertex. The boundary conditions of delta type are motivated by, as I said, continuity of the wave functions and a balanced flux duration for the derivatives. So this is actually a conservation of charge, so to speak. Boundary conditions of delta prime type imply continuity of the fluxes. The surface current density is the same in all three edges at the intersection. So one is actually conservation of the current, delta prime, and the other is conservation of charge, delta type. When Z equal to 0 in the delta boundary condition, you recover Kirchhoff's rules. And this is actually what is implemented by Nakajima and collaborators in their study. And it's equivalent to charge conservation at the vertex. So when Z is different from 0, the charge is not conserved, but it measures the difference of charge at the vertex. In the boundary conditions of delta prime type, when lambda is equal to 0, we obtain a Kirchhoff type rule for the self-induced magnetic flux. So it's kind of conservation of the magnetic flux. Now, both sets of boundary conditions correspond to all the self-adjoint extensions of this formal operator, which is Schrodinger operator on each edge on the star graph. I will talk about this later on. Now, we are interested in stationary solutions of the sine-Gordon model posed on a Y graph. So these actually are stationary solutions of kink or anti-kink type, which are the usual solutions, traveling wave solutions for the sine-Gordon equation on the whole real line. So you can recast the sine-Gordon model as a first-order system via the standard change of variables. Vj is going to be the derivative of uj with respect to time, and then you have this evolution equation for Vj. And we're interested on the flow of this sine-Gordon model around solutions of a stationary type which have this form. Uj is going to be a profile in X, and Vj is going to be 0. So phi j is actually the profile of these kink or anti-kink profiles, and it's a solution of the sine-Gordon equation, stationary sine-Gordon equation. Satisfying, of course, the boundary conditions either of delta or delta prime type are the vertex. So our motivation is to study these solutions, to describe these solutions. Do they exist? And most importantly, more importantly, to decide whether they are stable or not. So let's talk about some preliminary material in order to study this problem. First, some notations, of course. Suppose that you have A, which is a closed densely defined symmetric operator on a Hilbert space. The domain is going to be denoted by D of A. The deficiency index or deficiency indices of A are denoted by n plus or minus, which are the dimension of the kernel of A adjoint minus plus I times the identity. The number of negative eigenvalues, counter multiplicities, which is the Morse index of A, is denoted by n of A. And we work on standard energy spaces, Lebesgue spaces of L2 in the real line. HM will denote classical Sobolev spaces on a one-dimensional domain. And in the case of a junction graph of Y type, we are going to parameterize the edges, which is parameterized by the edges. We have to define the energy spaces as the direct sum of the Sobolev spaces on each ray. So, for example, the HM space on the graph is going to be the direct sum of the Sobolev spaces HM on minus infinity to 0, which is the first edge, plus two copies of HM in the other array, which is from 0 to plus infinity. And the same for the standard Lebesgue spaces. So let me recall and mention some classical results on extension theory for symmetric operators, which are needed actually for many of the proofs. So let me start with the classical von Neumann decomposition. If A is a closed symmetric operator, then the domain of A star of the joint is this direct sum, the domain of A plus n minus I and A plus I, where n plus or minus I is actually the kernel of a joint minus plus I identity. And you have, of course, this decomposition. The second result that will be used is the following. Suppose that A is a densely defined lower semi-bounded symmetric operator bounded by M, okay? And suppose that this operator has finite efficiency indices equal to K in the Hilbert space H, for example. If you have a self-adjoint extension of A, we denote by A hat, then the spectrum of A hat in minus infinity M is discrete and consists of, at most, chi-eigenvalues counter multiplicities. This is also a result. You can find it in the book by Druid and Simon. The second result that is going to be used is the following, proposition number 2. Suppose that A is a densely defined closed symmetric operator on a Hilbert space with equal efficiency indices. All self-adjoint extensions A theta of A can be parameterized by a real parameter. So this is a characterization of the self-adjoint extensions of this operator. The third proposition is can be found in the book by Naimark, second volume. All self-adjoint extensions of a closed symmetric operator, which has equal and finite efficiency indices, have one and the same continuous spectrum. Finally, proposition number 4 is like a combination of the previous ones in order to characterize the self-adjoint extensions of a Schrodinger type operator posed on a graph. This is the particular, I have to make a comment here, this is the particular case of delta boundary conditions. There is a similar result for delta prime boundary conditions, which I do not include here, but this is only for delta boundary conditions. And it goes as follows. Suppose that you have a closed symmetric operator, which is the this diagonal matrix operator on this domain, which actually resembles delta conditions, Dirichlet delta conditions, of course. Then the deficiency indices are equal to 1. And all the self-adjoint extensions of the operator, let's suppose that we call it JZ and D of JZ, when Z is the parameter defined in the delta boundary condition, are given by the operator, just like that. I mean, the application of M on this domain, which is the delta boundary condition type. I will not say anything about the proof of this. This is can be you are referred to the paper by Jaime Angulo and myself, 2021. Okay, so let's start with the instability theory. With first with delta interaction. I will focus mainly on the delta interaction, and I will gloss over many of the details in the case of delta prime interaction, just to give you an idea of what are the main ingredients, the key ingredients to prove that these profiles are unstable. The ones that we wrote down actually. So first, we have to consider the energy space. The energy space associated to the sine-Gordon equation with delta interaction is precisely this one. This is the energy space on the Y graph of type 1, okay? And we have to verify that the Cauchy problem associated to the sine-Gordon is well posed in this energy space. So this is the first result, which is the local well posedness of the sine-Gordon model on a Y-junction graph with delta interaction type at the vertex. So for any initial condition in the energy space, E cross L2, there exists a local time such that the sine-Gordon equation has a unique solution with this initial data. And for each t0 between 0 and t, this map, which goes from the initial data to the solution, so the data solution map, is at least of class C2. Okay? And so we have a strong solution to the sine-Gordon model. The proof of this is not tough, actually follows standard arguments, but it's delicate. So we need to be very careful about certain details. And these details are actually explicit resolvent, explicit characterization of the resolvent and the application, a direct application of Lummer-Phillips theorem in order to obtain the semigroup. So you recast the system in vector form. So you can actually, because of the structure of the equation, you can write it like this. This is like a symplectic or a matrix applied to this operator E. The nonlinear terms are comprised in this function f. So you put it in diagonal form when f is actually the diagonal matrix linear operator. Linear. Okay. So you consider this operator fz defined on the delta interaction domain. So this is the formal operator, and then you have to define it on the delta interaction domain d of fz, which is actually the one that defines boundary conditions of delta type. So the first step is to perform the spectral analysis of this operator. And you can show actually that for a z negative, f of z has precisely one negative simple eigenvalue. If z is greater or equal than 0, then fz has no eigenvalues. And the essential spectrum is all absolutely continuous. Next, you need an explicit characterization of a resolvent of the operator J times E. I didn't write down the explicit form of the resolvent, but these explicit analytic expressions for the resolvent are needed in order to obtain this representation of the resolvent operator in terms of the resolvent of Fz. Then you have an explicit formula for the semigroup, and from local standard, from standard arguments, Banach's fixed point theorem, essentially, you can prove that there exists a local solution. The implicit function theorem, thanks to the smoothness of the nonlinear term f, implies a smoothness property of the mapping data solution. So that the map that goes from the initial data to the solution is at least of class C2. Now, the next question is, what are the waves that you're going to study? So we need to construct these kink or anti-kink profiles. So let's suppose that you have specified the physical parameter z that defines the boundary conditions on the graph. So you can look for static solutions of this form, which actually resemble the kink solutions of the sine-Gordon equation on the whole real line. So for the first edge with negative x, then you simply change the sign, but you have actually a kink, which is 4 times the arctangent of exponential of 1 over c1 x minus a1. a1 and ai are constant to be determined. And on the positive edges, you have a classical kink. So we look for solutions of this form. Of course, this solution is a static solution phi, is subject to the boundary conditions of delta type. So if you play with the boundary conditions of delta type, from the conservation of the charge, you have this relation here between the A's and the C's, the speeds on each edge, and excuse me. From the other boundary conditions, you get this relation between the A's, the Z, and the parameter, the physical parameter Z. So actually, the physical parameter Z is a parameter that is going to determine the dynamics. It's going to determine everything. So from these conditions, after analyzing this function, you can see that Z has to is bounded between minus the sum of all the velocities, comma 0. So this is a constraint on the physical parameter Z. So now we use these relations in order to construct our solutions. So we proceed by cases. So the first case is when Z is between these two numbers, the sum of the C minus the sum of the CJs and minus 2 over pi, the same sum. And you obtain the signs for the parameters A. You obtain that phi A double prime is positive, phi 1 prime is positive, and phi prime J is negative. For J, this is 2 and 3. So this is called a profile of tail type. Tail type because the kinks arrive at the vertex and they just go down, okay? So they are, as you know, there is continuity at the vertex and then they go down. Let me show you a picture of this. So this is the Y-junction graph. This is the E1 vertex edge, sorry, from minus infinity to 0, and then the other two positive edges, E2 and E3 from 0 to plus infinity. And then you have these kinks that go down. They coincide at the vertex and they go down on each side. We put this shadow or shaded graph in order to tell you that the energy is finite. Actually, these solutions belong to the energy space under consideration. So this is the first case, a configuration of tail type. We call it tail. Case B, in the case when Z is exactly minus 2 over pi, the sum of the velocities, so the other boundary value, this implies that the A's have to be 0, the three of them. And in that case, we have we call it a smooth profile. It's not actually smooth, but they coincide, the derivatives coincide at the vertex. So this is of this type. And the third case is when Z is between this value and 0. So in that case, A1 changes sign and A2 and A3 are positive now. And then you have actually that phi prime 1 is positive and the other derivatives are negative. So the profile has like a bump. So we call it, the profile is a bump type. And it has this shape, as you can see. So these are the three types of stationary solutions for the sine-Gordon model on a Y-junction graph with delta conditions and of kink type. Recall that we started from these ansatz. So all the profiles are of kink type. Okay, so now the question is, are they stable or not? So these are specific solutions, explicit solutions of the model, and we are going to determine whether they are stable or unstable under small perturbations as solutions of the PDE on the graph. So according to custom, you start by linearizing your nonlinear problem around this solution. So you rewrite the sine-Gordon model again in vector form with these operators, J and E, and the nonlinear terms are comprised in this F as before. But now we will consider the operator F on this domain, which is the delta interaction domain, and we will define a perturbation. So the perturbation is going to be the solution minus the profile and linearize around the perturbation. So if you linearize around the perturbation, you now have an operator which has almost the same form. It's the same J times this calligraphic E, but now this calligraphic E is actually the linearization around the profile. So it's like a Schrödinger operator with a potential given by 1 minus sine, right? Evaluated precisely at the profiles on each edge. So this is going to be the operator double star. And actually, this operator is the one that contains all the information. So we need to study the spectral properties of this operator in order to conclude the spectral properties of this whole operator JE. Once again, the domain of L is precisely the domain of Fz, which is the domain of delta interaction with intensity Z, and the domain of the big operator J times E is actually the domain of Fz cross or times L2. Notice that in the case of the kink profiles, these solutions belong to this domain. They have finite energy. So we proceed with the spectral instability analysis. We actually going to prove that these coherent structures are spectrally unstable. And for that purpose, we have to establish an instability criterion. So as it is customary, you start the stability analysis by finding growing mode solutions with a real part of mu positive in order to conclude instability. So you say that the stationary vector solution, which is the kink profile, is said to be spectrally stable for the sine-Gordon model if the spectrum of J times E satisfies this property, which is contained in the imaginary axis. Due to the structure of the problem, even the sine-Gordon equation on the real line has this property. There is a symmetry of the spectrum between the real axis and the imaginary axis. So the only way that you can have stability is if the spectrum is contained in the imaginary axis. Otherwise, the stationary solution is said to be spectrally unstable. So this observation is exactly what I just mentioned. It is a standard to show that the point spectrum is symmetric with respect to both the real and imaginary axis, and the essential spectrum is contained in the imaginary axis. So to prove that something is spectrally stable is equivalent to prove that the point spectrum of J times E belongs to the imaginary axis, and to prove that some structure is spectrally unstable is equivalent to prove that point spectrum contains some eigenvalue with a real part of with a positive real part. Okay. So now the eigenvalue problem that we are going to study is reduced to this one. Okay, so this is the linear instability criterion for the sine-Gordon equation on this graph. Let's suppose these three hypotheses. Let's suppose that JE is a generator of a C0 semigroup. Second hypothesis, let's suppose that the matrix operator L that I just showed you, defined on a domain, is self-adjoint. And number three, suppose that this operator is invertible with Morse index equal to 1, and such that the spectrum of L is some isolated eigenvalue lambda 0 union this set, which is contained in an array, with R0 positive and lambda 0 negative. So this means that it has one negative eigenvalue and the rest of the spectrum is positive away from 0. So this is the criteria that we established. Suppose that these three assumptions hold, then the operator JE has a real positive and a real negative eigenvalue. The sketch of the proof of this, well, is based on the work by Lopez, who was the first who observed this, and the following result on closed convex cones by Krasnodębski. The theorem by Krasnodębski says the following thing: if you have a closed convex cone on a Hilbert space such that there are continuous linear functional and pi and a constant a such that pi of u is greater or equal to a times the norm of u, is coercive on the closed convex cone, if T is a bounded linear operator that leaves K invariant, then it has an eigenvector associated to the non-negative eigenvalue. So we apply this result to the following non-empty closed convex cone in our context. And then you can show that this non-negative eigenvalue has to be different from 0. And from the symmetry, you have that both minus and minus z and z are actually eigenvalues. So this is how you prove this criterion. So this is the main instability result for these waves of kink type with delta condition. It says the following: suppose that Z is in the domain of existence, right? Then all of them, the smooth family of stationary profiles of kink type, are spectrally unstable. This is an instability result for this kind of solutions. So how does the proof go? Well, you have to go on a case-by-case basis, and it's based on calculation of the Morse index of the operator. So we apply the criterion to the operator L, and this is enough to conclude instability because of the criterion. So the first result is that for every Z under consideration, the kernel of LZ is actually 0. So this follows from Sturm-Liouville theory on half lines. So you can suppose that you have an element of the kernel, and then you prove that it has to be 0 by doing some calculations on a case-by-case basis. Of course, when Z is in between certain values. Okay, I will skip these. Then, depending on the value of Z, then you can conclude that the solution has to be 0, and therefore the kernel has to be 0. The second result is actually the calculation of the index. So let's suppose that Z is in between minus the sum of the speed and the boundary value, which is minus 2 over pi, the sum of the speeds, inclusive, okay? Then the index has to be equal to 1. How do you show that? Well, it follows from the extension theory for symmetric operators. From proposition 4 that I showed you before, this family represents all the self-adjoint extensions of the closed symmetric operator M0 D of M0, which is the linearization about the wave on each edge with the Dirichlet boundary conditions. Okay, so this family are all the self-adjoint extensions of this closed symmetric operator. So you can show that actually this operator is greater or equal than 0, and you can compute the product of the M0 applied to our wave, and you can see that the integral terms are non-negative or equal to 0 if and only if you have that the profile is equal to 0. Okay, and in this fashion you can show that this operator is non-negative, and all the self-adjoint extensions of this operator satisfy that the index is less or equal than 1 because of proposition 1 that I showed you before. So then from minimax principle, you can arrive that it has to be equal to 1. And in this fashion, you show that the index is equal to 1 in this regime of the parameter Z. The third lemma is actually the same result, but in the rest of the domain of Z. So you have the same result, that the index is equal to 1, for Z strictly greater than minus 2 pi over times the sum of the speeds. And this result, excuse me, follows from analytic perturbation theory. So from lemma 1, you actually have that if you name is Z star as this threshold value, then the index is equal to 1. So actually, you have a continuous mapping from Z in this domain, in the whole domain, to A1, when A1 is negative for Z star less than Z, 0 if Z is equal to Z star, and positive if you are on the other side. So you can prove actually that these operators LZ converge to LZ star as Z equals to Z star in the generalized sense. So that this means in the graph sense, the distance of the graph goes to 0. No? Now you can show actually that the index is equal to 1 for Z in a perturbed neighborhood of Z star for delta 1 sufficiently small. And then using a classical continuation argument based on the risk projector, the integral of the resolvent, etc., you can show that the index is equal to 1 for all Z between Z star and 0. If you define omega as the supremum of eta, such as eta is, the index is equal to 1 in this regime, using the risk projectors, you can show that omega is 0. So in this fashion, you show that the index remains to be 1. So if you apply these 3 lemmata, 1, 2, and 3, you can end the linear instability criterion, you obtain the result that all these stationary waves are actually unstable, spectrally unstable. Now, you can consider also other class of solutions, which we call of kink or anti-kink type. For simplicity, let's assume that all the velocities are equal to 1. And now on the first edge, you suppose this limit. You suppose that the profile goes to 2 pi. Okay, so this is actually an anti-kink solution on one edge, and then you couple with a delta boundary condition to 2 kinks on the other 2 edges. So I will gloss over many details here. By a similar analysis on the boundary conditions, you can show that the parameter C actually has to belong to -1, 0. And here, the observation is that these stationary profiles do not belong to the energy space H2. They actually, especially the anti-kink solution, has infinite mass. So they do not belong to the space, but you can linearize around it and consider perturbations of finite energy. For example, if you consider Z in a certain regime, you obtain what is called it's a solution that looks like 2 left translated anti-kinks on the line. Let me show you the picture. It's like this. So look at the anti-kink on the E1 edge, has an infinite mass, and it's coupled with 2 kinks on the other two edges. Again, playing with the parameter Z, there is a threshold value in which you have this configuration, and for Z on the other side, you have this configuration. Now, using more or less the same techniques, you can prove that for all the parameter values between -1 and 0, this smooth family of stationary profiles are spectrally unstable, even though they don't belong to the energy space. Okay. And what happens with the delta prime interaction? Well, I will go fast on this because my time is running out. But here the energy space with delta interaction is simply H1 times L2 on the graph. And you can apply similar arguments to prove the local well-posedness of the problem of the sine-Gordon equation on the Y-junction graph, but now with delta prime boundary conditions. And again, you propose families of kink profiles or anti-kink profiles. Again, everything will depend on the value of the physical parameter lambda. Lambda in this case will belong to -infinity to minus the sum of the speeds. And depending on the value, on the location of lambda, you will have the 3 different configurations. Let me jump to the figures, which are more easy to take a look. This is a configuration of bomb type. Remember now that there is no continuity of the wave function, but continuity of the fluxes. So now, as you can see, these waves are discontinuous at the vertex. In this case, these are configurations with finite energy. This is the case for lambda very, very negative. And when lambda approaches a threshold value, then you have a configuration of this type and of tail type when lambda belongs to this open set. Okay. And similar spectral techniques can be applied to obtain the following result. These kink type solutions are actually spectrally unstable if certain conditions are satisfied. In the case from minus infinity to the threshold value, you have the same conditions here, A1 and C related like this, and plus a condition that all the velocities are the same. Excuse me. And for the rest of the domain of existence, you need only these conditions. Okay. And you can apply also the same techniques in order to prove that profiles of kink and anti-kink type are also unstable. For simplicity in this analysis, you suppose that all the speeds are the same, and then the domain of existence for lambda are simplified, of course. And then you have, for example, these configurations: an anti-kink arriving in a non-continuous way for the phase, but continuous for the flux, coupled with two kinks, and the same with the other parameter values for lambda. The spectral study yields that these solutions are also spectrally unstable. Okay, let me conclude my talk by discussing some issues. These results constitute a nonlinear instability theory for static solutions to the sine-Gordon equation on a Y-junction graph for both delta boundary conditions and delta prime boundary conditions. A few remarks are in order. Why did I write nonlinear? Well, you can conclude nonlinear instability from the linear stability result, thanks to an early result by Henry and collaborators, in which if you have precisely this regularity of the data solution map, which has to be C2, then you can prove that iterations of the nonlinear map are actually controlled by the unstable eigenvalue, and then you can apply this nonlinear map repeatedly in order to conclude that these stationary profiles are unstable under the flow of the sine-Gordon model on the graph. So actually, the conclusions are of nonlinear nature as well. The other remark that I want to make is that we only prove instability of a certain kink or anti-kink profiles that we could construct. These solutions are difficult to construct. So we only prove the instability of those. So the main question is, are there stable structures? And let me mention a paper by Susanto and Van Gils. It's an applied paper based on a previous paper by Kogan and collaborators. They consider a delta prime interaction with lambda equal to 0. And they proposed a shifted profile. It's like a kink profile, but shifted. So they add minus pi over 2 at the vertex. And this structure is apparently stable, according to the numerics. There is no proof of this, but it's apparently stable. So this is an open problem. So the first conjecture is that the structure the minimizer of a certain energy? This is something that we are working on. And the second conjecture, are there particular structures that minimize Z and delta and lambda energies for delta or delta prime boundary conditions? This is also work in progress. And with this, I conclude. I thank you for your attention. These are the references of the paper with the Professor Angulo Pava, 3 papers that contain all this theory. And thank you so much for your attention.
Thank you very much for a very interesting talk. Now, if there are questions.
Yes.
Yeah, go. There are questions. I wanted to ask you something which is not directly related to your talk, but if you know results on, for example, on particular trees, equation and graphs.
There are some. I don't know exactly the reference, but let me. No, I don't know exactly the reference, but I'm sure there are some. On graphs, I've seen mainly NLS equation, nonlinear Schrödinger, and some shallow water models on graphs. And for the KDB, I'm not quite sure, but I'm sure there are. I'm sorry, I cannot tell you the exact reference, but I'm sure there are some.
And if for sine-Gordon equation, if there are some kind of inverse problems also on graphs.
I don't know. But that's a very interesting question, because then you can perhaps you can apply all the properties of the sine-Gordon equation and on the graph, but I'm not sure. I really don't know.
At least to recover the geometry, for example. Graph.
Exactly.
So
but I don't know any reference. No.
If there are questions or comments.
May I have one?
Yeah, please.
Just one question about terminology. As I understand, you have kink and anti-kink situation, kink and anti-kink solution only if you have also kink and anti-kink statement of your problem, right? So the one includes the other, right? You have either kink or anti-kink.
Right.
So there is no relation between them.
They are the classical solutions of the sine-Gordon on the whole real line. So one is the kink that has the plus sign, so it goes from 2 pi and then, sorry, it's the other way around. It goes from minus infinity and then it goes to a constant value, and the other one is reversed. It goes from the constant to 0. So
Great.
So this is just the only difference. And then you can make combinations with different H's. And that's it.
Thank you. More questions? Fortunately, I cannot see here. If there are some.
Yeah, it's hard to see from mobile. The hands.
But there are no hands. I can see it from the computer.
So if there are no more questions, then
No questions.
Yes, no questions.
No questions.
Okay, thank you very much. So if there are no questions, thank you very much, General. Thank you.
Thank you very much for the invitation, and it's a pleasure to finally meet you, Alexey, and it's a pleasure to meet you, Vladislav, and thank you all for your kind attention.
Thank you.
Thank you very much.
For the invitation.
Goodbye. Thank you.